Good morning. We will start with 3.5 rational functions today. And I assume that you have watched the corresponding lecture videos. Let me see which lecture video is supposed to be. I think it should be lesson 12. Lesson 10 and 11. You should have watched lesson 10 and lesson 11. Today, I would like to cover 3.5 and a bit of 4.1 if possible. Okay, let's start. 3.5, that's on rational functions. And let me remind us of the notation. A rational function is a function which is a quotient of two polynomials. Now, I use these notations especially in my class. Okay, I will use px as the polynomial on the numerator and qx as the polynomial on the denominator. Okay, and if px and qx has common factor, then R star x equals to P star x over Q star x, that's my notation, be the simplified form. Where the common factor cancels. Now, also, I will use this notation for px. Px will be a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 2x squared plus a sub 1x plus a sub 0. Basically, what I want to say that n is the degree of px, and the coefficients, we use notations a subscript. While for qx, I will use b and m. So b sub m x to the m, b sub m minus 1 x to the m minus 1. That's b2 plus b1x plus b0. Where the degree of qx is m, and b sub j is the coefficients of qx. Okay, let's say that's the rational functions, and that's the setup. And then things that we will work on, the question we need to be able to answer are first the domain, that is all real numbers except the zeros of qx. That's the domain. Then the y-intercept is 0, a sub 0 over b sub 0. The constant of the numerator over constant of the denominator. You see, when x equals to 0, this basically becomes just a sub 0 and becomes b sub 0, right? So the y-intercept will be the ratio of the constants, basically. Okay, of course, with as long as b sub 0, the constant of the denominator is not 0. Yeah, because if b sub 0 is 0, it means x equals to 0 is not in the domain. Okay, how about the x-intercept? X-intercepts are the real, maybe I use C. I use C. C, comma 0, where C equals to real 0 of P star X. Real 0 of P star X in the domain. In the domain. Yeah, so you will see later on. Oh, of course, we do problems regarding this. Okay, but what I meant by the real 0 of P star X, the simplified form. The simplified form. Okay, the 0 of the numerator of the simplified form, but it still have to be in the domain. And then we have vertical asymptote, part D, vertical asymptote. Yeah, I'm summarizing the lecture, basically. Vertical asymptote, that's a vertical line, so it is x equals to C, where C is the real 0 of Q star X. Okay, the denominator becomes 0. Okay, and that's the vertical asymptote. Now part E, horizontal asymptote. Follow this rule. First, if the numerator, the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is given by y equals to 0. If the degree on the top is equal to the degree at the bottom, then horizontal asymptote is given by y equals to the ratio of the leading coefficient over leading coefficient. And if the degree of the numerator is greater than the degree of the denominator, no horizontal asymptote. How about oblique asymptote or slant asymptote, we usually call that. Is given by y equals to mx plus b, where mx plus b is the quotient of p star x over q star x. If you divide the rational functions, okay, then you get a linear function, a linear equation. Now that linear equation is the slope slant asymptote. But this is only if the degree on the top is 1 more than the degree at the bottom. Why when the degree on the top is greater than the degree at the bottom, no horizontal asymptote? Let's see, for example, we have x squared plus 4 over x minus 5. You see the degree on the top is 2, degree at the bottom is 1, right? Okay, so because the degree on the top is more than the degree at the bottom, then as x goes to infinity, this goes to infinity a lot faster compared to this one. It will not go to a constant. Okay, in fact, if we divide the top and the bottom by x, we will get x plus 4 over x, 1 minus 5 over x. And when x goes to infinity, this will be infinity plus 0 over 1 minus 0. That's infinity. Okay, it becomes horizontal asymptote if it goes to a certain constant. So let's say this is the horizontal asymptotes, right? Now then the graph will go to that number the further you are to positive infinity or the further you are to negative infinity, then the value of y is approaching that specific number. But if the degree on the top is greater than the degree at the bottom, then when x goes to infinity, the numerator will go to infinity faster compared to the denominator. As we can see with this analysis here, if we divide the top and the bottom by x, right? Okay, when we divide the top and the bottom by x, then you will see x on the top, but the rest will eventually goes to constant or 0. So we still have that infinity. That's the reasoning behind why if the degree on the top is more, then we don't have horizontal asymptote. Yeah, we have horizontal asymptote if, as we go to infinity, the value of the function approach a certain number. Now here, it goes to infinity or maybe negative infinity. Okay. Now, what I will do now next is I will do problems from our textbook. Again, my assumption is you already watched lesson 10 and lesson 11. Okay. Yeah, my assumption is you already watched lesson 10 and lesson 11 on rational functions. And I will just do problems today. Now let's start. Let's take a look, for example, number 14. Number 14. I will try to do as much problems as possible with varying difficulties, like it gets more and more difficult. Okay, now, but at the same time, however, we still need to pay attention to the details. Like in the end, we need to graph them. Okay, in the end, we need to graph them. Okay, let's see number 14, where we have let fx equals to 4x over 2x minus 5. And that's our rational functions. Okay, no common factor, right? No common factor. So let's answer those questions. And then finally, we will graph them. Okay, we may do the sine graph first and then do the full graph. But we will have other analysis after these 6 questions that we need to answer, like domain, Y-intercept, X-intercept, vertical asymptote, horizontal asymptote, slant asymptotes. Maybe after that we have sine graph or the full graph. Do we have any horizontal asymptote intercept in, right? The graph intercept at horizontal asymptote maybe, and those further, basically those further details. Okay, so part A, what is the domain? The domain question is a question that we know how to answer already since basically the second or the third week of class. Okay, the domain is all real number except the zeros of the denominator, right? We have this kind of question in your test one. Okay, now part B, what is the y-intercept? Then you take a look what is f0, basically, right? F0 is 0 over -5, that's 0. So the y-intercept is 0, 0. That's easy. How about x-intercept? You look at the numerator, okay? It's already in simplified form, right? Okay, you look at the numerator, set it equals to 0, so x equals to 0. And it is in the domain, right? It is in the domain. X equals 0 is in the domain, so that's 0, 0. Okay, part D, do we have horizontal asymptote? Oh, vertical asymptote first. Do we have vertical asymptote? Yes, vertical asymptote is given by x equals to, remember that's a vertical line, so you need to write it as the equation of a vertical line. Okay, x equals to 5 over 2. Okay, most of the time, but not all the time, that the vertical asymptotes is equal to the number you need to exclude. Most of the time, not all the time, not all the time. Okay, not all the time. And then part E, do we have horizontal asymptote? The degree on the top is 1, the degree at the bottom is also 1. So the horizontal asymptote is given by y equals to the leading coefficient on the top over the leading coefficient at the bottom. Okay, so y equals to 2. That's the horizontal asymptote. Now, once we have horizontal asymptote, then we don't have vertical, we don't have oblique asymptote. Okay, now let's take a look on the sine graph. Now, the purpose of sine graph is to provide us a more detailed view, but not the full detailed view of how the graph will behave above or below x-axis. Now, don't forget that we need to incorporate all critical numbers, right? We have x equals to 0, that's the 0 of the function. 5/2 is a critical number that make it undefined, right? It is not in the domain, right? And then we will do sine graph when x equals to 1, let's say. When x equals to 1, we will get 4 over -3, that's negative. It means in the interval from 0 to 5 over 2, the graph will be below x-axis. Okay, and then 5 over 2 is a critical number with multiplicity of 1, so this is change the sign. This also change the sign. Okay, now let's sketch the graph without full detail yet, but we actually has most of the detail right now. How do we know plus minus plus? You do the testing point. You can do the testing point. I did testing point on x equals to 1. When I did x equals to 1 into this function, I get 4 over -3. So that's negative. And then 5 over 2 is a critical number with multiplicity of 1. So we change sign. 0 is a critical number with multiplicity of 1, so we change the sign. Now, other than that, you can actually test a point. Let's say when x equals to -2. So 4 times -2 over 2 times -2 minus 5, you will see that's negative over negative, which is positive. Okay, and when x equals to, pick a number here, let's say x equals to 5, and you will get 20 over 5. That's a positive. Okay, so there are two ways of doing the sine graph, the sine of a certain interval. You use the idea of critical number, which in my opinion faster, or just go back to the traditional way, testing point. Okay, but I prefer you to use critical numbers because it's a lot faster. You just need to get the sine of one interval, and then you use that to jump around. And after all, we learned that already, even before test 1, right? That's why we learned that at that time. Okay, remember, some of you still want to use your textbook method. Okay, you want to use your textbook method, go ahead. You won't have enough time. Okay, now let's start sketching the graph. Okay, we will not sketch the graph to in scale. Okay, we will just sketch the graph such that all the details are actually put in. The X-intercept and Y-intercept happens to be the same, 0, 0. Okay, we have vertical asymptote 5 over 2. Vertical asymptote 5 over 2. So that's a vertical asymptote. X equals 5 over 2. And we have horizontal asymptote Y equals to 2. Again, I don't draw it to scale. And then we actually have pretty much nothing else, right? But we know we have horizontal asymptote, which means the graph must come from horizontal asymptote here. Okay, either it goes up or goes down. Okay, but then if we think about that, then it's supposed to go down. Why? Because we have, if it goes up, okay, let me start by saying this. We must start from the horizontal asymptote on the left-hand side. Now, the issue is, do we go up or do we go down? Now, there are two ways to figure out. You do testing, you pick some coordinates here to plug in the numbers, okay? But with some thinking, you will see that it will be the one going down. Why? If it goes up, then you must have an Y-intercept there, and you don't have an X-intercept here. Okay, so it won't be this one. Is it okay? So it won't be this guy. It has to be the one below. And because x equals to 5 over 2 is a critical number with multiplicity of 1, then the graph will change from negative infinity from the left-hand side. It becomes positive infinity from the right-hand side, and it goes back to the horizontal asymptote. That's what the graph will look like. Okay, and notice that the sine, this actually follows the sine graph, that between negative infinity to 0, it will be above x-axis. From 5 over 2 to infinity, that is still above x-axis, right? Yet, between 0 to 5 over 2, it is below x-axis. Okay, so for now, we know that's what the graph look like. Okay, but if we want to see more details, we can. For example, one of the detail that we will need later on is, does the graph intersect the horizontal asymptote? How do we check that? How do we check if the graph intersect horizontal asymptote? Then set them equal to, set the equation, set the function equal to the horizontal asymptote. Okay, now we have the function 4x minus 2x minus 5, set that equals to the horizontal asymptote, which is 2. Okay, and then solve for x. So we get 4x equals to 4x minus 10. So 0 equals to negative 10. That's a contradiction. Right? So no horizontal asymptote intercept. The graph will not intersect horizontal asymptote. Now from there, then you will see that we can actually say the domain, the range of this function. Then we can say, not all the time we can answer that question, but in this question, in this function, this question, we can find the range. One of them by you looking at the graph, right? It comes from very, very close to the horizontal asymptote, but not touching it. Well, because if you touch it, then you must have find it here, right? You must find such x, but we find out that no, it doesn't touch horizontal asymptote. And likewise here, it doesn't touch horizontal asymptote. Now, if you take a look, then the range will be all real, number except 2. That is all real numbers except 2. Okay, now another method to find the range is, not always work, but works a plenty of time. Another method to find the range is to solve for x. So you isolate x by itself and read the y. For example, in this case, we know that y equals to 4x over 2x minus 5, right? Now try to solve for x. You modify this such that you have x equals to something. Okay, then from there we can see what kind of y we are allowed to put into that equation. So let's show the details. So multiply by the denominator, y times 2x minus 5 equals to 4x. 2xy minus 5y equals to 4x. I will move the 4x to the left-hand side and 5y to the right-hand side. Factor the 2x. So x equals to 5y over 2 times y minus 2. Now from there you see what kind of y you are not allowed to put in. Y cannot be 2, right? Now then the range will be all real numbers except 2. Okay, well, anyway, that's the further detail of this graph. That's the further details of this graph. Now from here, from the graph, you can see that as x approaching 5 over 2 from the left-hand side, when we approach x equals to 5/2 from the left-hand side, okay, the function is approaching, the value of the function is approaching negative infinity. On the other hand, as we approach 5/2 from the right-hand side, when you approach from here, right, but going to the left, approaching 5/2 from the right-hand side, then the value of the function is approaching positive infinity. Okay, now this is the first question, number 14. Let's see number 18. But again, I don't remember which question I have done in my lecture. I just don't want to repeat the same question again. But I don't think I did those questions though. But let me see. Number 18. Number 18, we have this function fx equal to, let me use black color. Number 18, let fx equals to, they already factor it for us, which is nice of them. 5x plus 3, x plus 1 over 3x minus 7 times x plus 1. Now, notice that this is the original rational functions, okay, which simplifies to be 5x plus 3 over 3x minus 7 for x not equals to -1. Okay, what I want to say is this. What we did usually in algebra is we just simply cancel this, right? Okay, and we say that this guy equals to this. Actually, they are not exactly equal to. They are not exactly equal to. Okay, they are only equal to each other as long as x is not equals to -1. Okay, let's say x equals to 2, then the value on the guy on the top is the same to the value at the guy at the bottom. Okay, as long as x is not equals to -1. But once x equals to -1, then the value on the original function f -1 is undefined. Okay, while this one here, when you plug in x equals to -1, it will give you a real number. Okay, so this is the one we call the simplified version, f star x. That's what we call the simplified version. Okay, f -1 is undefined. F star -1 is -2 over -10, which is positive 1/5. Okay, that's the difference. Okay, now then it is undefined for x equals to -1. Okay, let me circle that again and call that this is f star x. They are not exactly the same function. They are not exactly the same function. Fx and f star x are same only when x not equals to -1. Okay, so let's say this is the graph of f star x. It is undefined at 7/3, right? Now, the graph of fx will be the same graph. The graph of fx will be the same graph. but we have extra undefined at -1. Now that's the whole. While what happened here will be a vertical asymptote. Okay, later on you will see that in detail. Okay, so one of the key part when you work with rational functions, you need to be able to factor them. Okay, now the rational functions I give you tends to be something easier to factor. You don't need to know how to use polynomial that we learn in 3.1 to 3.4. Okay, yeah, but you still need to know how to factor the basic factoring, the one that we learned in chapter 1. Okay, including difference of cubes, sum of cubes, grouping method, and so on and so forth. Okay, now, and we start, what is the domain? For the domain, of course, we look at the original function. The domain will be all real numbers except 7/3 and -1. Okay, so these are the zeros of the original function. And then, how about the y-intercept? Well, plug in f0. There'll be 3 times 1 over -7 times 1. That's -3/7. So the y-intercept is 0, -3/7. Any questions so far? Okay, how about the x-intercept? X-intercept, you look at the zeros of the simplified version. Okay, 0 equals to 5x plus 3, right? And then when you solve that, you will get x equals to -3/5. Okay, and -3/5 is in the domain, right? So the x-intercept will be -3/5, 0. Okay, so I use from the numerator of the simplified version. You can actually use the numerator of the original version. You can also do it this way. So 5x plus 3 times x plus 1 should be equals to 0. So we get x equals to -3/5 and x equals to -1. But I have to cancel x equals to -1 because it's not in the domain. Okay, so we cannot ask this person to be our MC because he is not even in the invitation list. He's not even invited to the party. How can you ask that person to be the MC, one important coordinate, right? Okay, so it's not that you strictly have to use the numerator of the simplified version. No, even if you do so, you still need to check against the domain. You always need to check against the domain. Okay, for that guy to be an important coordinate, right? That guy has to be in the domain. Okay, now part D. How about the vertical asymptote? Vertical asymptote, that's x equals to 7/3. That's the zeros of the denominators of the simplified version. Okay, so hold on, Thomas. -1 is not in the domain, but it does not become a vertical asymptote. Why is that? You will see later on, -1, it will become, I don't know precisely, but it will become a whole. Okay, and then you have a vertical asymptote at 7/3, like that, approximately. Okay, yeah. So even though both of them not in the domain, even though both 7/3 and -1 not in the domain, but 7/3 will be x equals 7/3 will be the vertical asymptote, and -1 will be the whole. Okay, because that's the one canceled, right? That's the one canceled. In fact, they cancel evenly, so that will be a whole. Okay, now one of the big question later on, of course, is x equals to -1 will be a whole. I think I should say at x equals to -1, there will be a whole. And the question is, what is the coordinate? What is the coordinate of that whole? We do it later on, okay? But for now, let's focus on the main story first. The vertical asymptote is x equals to 7/3. How about the horizontal asymptote? Do we have horizontal asymptote? Oh, both of them degree of 2, right? After we simplify it, it becomes degree of 1 for the top and the bottom. So the horizontal asymptote will be y equals to the leading coefficient over leading coefficient. Because we have horizontal asymptote, there won't be any oblique asymptote. Now let's answer that question, that extra question. What is the coordinate of the whole? We know it will be a whole at x equals to -1. Now, if you plug in x equals to -1 into the original function, you will get undefined, right? You will get undefined. Now, what you will do is you actually put it into the simplified form. You put it into the simplified form. Okay, so you use f star -1. You use that x equals to -1 that you cancel, you put it there. Okay, that will be the whole. So that will be 5 times -1 plus 3 over 3 times -1 minus 7. That's -2 over -10. That's 0.2. So the coordinate of the whole will be -1, 0.2. Does the graph intersect horizontal asymptote? Horizontal asymptote intersect? So suppose I want to ask that specific question, right? Then you set the simplified version, 5x plus 3 over 3x minus 7, set that equals to the horizontal asymptote. Okay, and solve it. Okay, now if we have no solution from here, it means there's no horizontal asymptote intercept. Okay, so 3 times 5x plus 3 equals to 5 times 3x minus 7. 15x plus 9 equals to 15x minus 35. That gives us 9 equals to -35. That's a contradiction. So no horizontal asymptote intercept. Okay, now let's start sketching the graph. I will start sketching the graph. Again, I will not graph it to scale. Okay, I will not graph it to scale. And there could be times I don't know if that will be above or below x-axis, which is actually not true. I can always find it out. But in case you cannot tell if it is above or below x-axis, then you can do the sine graph to figure out. Okay, Now let's put the details here. We see that the vertical, as a, you know what, I start from the y-intercept first. Y-intercept is 0, -3/7. Y-intercept is 0, -3/7. Again, I don't draw it to scale. So because I don't draw it to scale, I need to put the number there. Okay, and x-intercept is -3/5, 0. Okay, and then what else? We have vertical asymptote 7/3. Vertical asymptote 7/3. Let's say it's approximately here. We never intersect. The graph will never intersect vertical asymptote. Never. Vertical asymptote, you never intersect that. Okay, never intersect that. Okay, for vertical asymptote, the graph's supposed to look like this around the vertical asymptote. And that's why you call that vertical asymptote. Okay, it will be either one of those. It will go to positive infinity or negative infinity around 7/3, but there will be no value y associated to x equals to 7/3. Okay, now horizontal asymptote is 5/3. Horizontal asymptote is 5/3. So let's make it here. Y equals to 5/3. And we actually have a hole. The hole is at -1, 0.2. So -1 is to the left of -3/5, right? And then 0.2. So the graph will then be, well, if I start from horizontal asymptote, it will be slightly below that and go this way. It must look like that. Okay, it's supposed to be smooth here though. It's supposed to be smooth here. Okay, yeah, it's supposed to be smooth there. Let me try to make it smoother. Okay. Oh, you know what? I need to put the coordinates for that hole. -1, 0.2. Like that. So the graph looks like this. Okay. Now, even more details. How do we know when the graph is above or below x-axis? Now we did this before. You do construct sine graph on the rational function, in this case on fx. Okay, sine graph, we have a hole at -1 and critical numbers 0 at 3/5. Okay, and you will see, you can show the details later on, but it will look like this. Oh, hold on. I'm sorry, that's not true. This is plus here. This is minus. And then we have another critical number 7/3. That's undefined. This is plus. like that. That will be the sine graph. Now, to see if it is above or below x-axis, you do that against the original function. Is it negative 3/5? You're right. I happen to erase the negative. Yeah, I happen to erase the negative. Thank you. Okay, now, but the follow-up question, another further question, how do we know? How do we know when the graph is above or below horizontal asymptote? That's more interesting question. Is it 3/7? Is it 3/7? Is it 3/7? Negative 3/7 is the y-intercept, but vertical asymptote is 7/3. Yeah, vertical asymptote is 7/3. Okay, the vertical asymptote is 7/3. Okay. Yeah. Now then, how do we know if the graph is above or below horizontal asymptote? Then construct sine graph on fx minus horizontal asymptote. Okay. Now let's do that now. Let's do that now. Let's do that now, so that we know when will the graph above and below the horizontal asymptote. Okay. Now the function. Let me do it here. Let me do it here. So the function fx minus horizontal asymptote. I will create the sine graph for that. Fx is what's that? 3x plus 5 times x plus 1 over what's that? Oh, 5x minus 3. Sorry, I copied that wrong. This is 5x minus 3. And this is 3x minus plus 3. This is 3x minus 7, x plus 1. Now you subtract that with the horizontal asymptote 5 over 3. Okay, now again, our goal is to construct a sine graph. But for us to do that, we need to simplify this first. Okay, yeah, we need to simplify this first. So we will get, this is multiplied by 3 on the top and the bottom. Okay, and then here I will multiply by, basically I get the LCD. X plus 1. Okay, so the bottom I leave it like that. It's already in factor form. The thing is on the numerator, it is not in factor form. Okay, x plus 1 is the common factor. I will factor that out, but I have 3 times 5x plus 3 minus 5 times 3x minus 7. Okay, take a look, take a look. I factor this guy out. Instead of foiling that and then combine like terms and then factor back. Now here I see common factor x plus 1, right? I factor that out. So basically I do factorization by grouping here. Then simplify further, I will get x plus 1 times 15x plus 9 minus 15x plus 35. arithmetic over 3 times 3 minus 7 x plus 1. That will be 44. 44 times x plus 1 over 3x minus 7 x plus 1. So from there you see the critical numbers are x equals to -1 will give us undefined, right? And notice that x equals to -1 is a 0 with multiplicity of 2. 1 on the top, 1 at the bottom. And we have another critical number, x equals to 7/3, that will give us undefined. Okay, now when x equals to 0, let's do the critical, the testing point. When x equals to 0, we will get negative here. 5x minus 3, is it 5x minus 3? No, it's 5x plus 3. Yeah, it's 5x plus 3 and then 3x minus 7. Okay, and then coming back here, 7/3 is a critical number with multiplicity of 1, so I change the sign. -1 is a critical number with multiplicity of 2, so I don't change the sign. Now, how do we interpret this? It means that along this interval here, the graph will be below horizontal asymptote, and when it is positive, it is above horizontal asymptote. Now compare that to the graph we have, right? Okay, between -infinity to -1, -infinity to -1, -infinity to -1, it's below horizontal asymptote. Between -1 to 7/3, it is still below horizontal asymptote. And then from 7/3 to positive infinity, it is above horizontal asymptote. Where is 3 first 3x minus 7x plus 1? Oh, I missed the 3 at the bottom, huh? Like this. Right? But the sine graph will be the same, right? Yeah, the sine graph will be the same. Okay, now that's if we want to do the analysis if or when the graph is above or below horizontal asymptote. Okay, now sometimes it's about the details at the far end behavior. Sometimes we don't know, we can't really decide if the graph actually start from below horizontal asymptote and go that way, or it's actually start from above and cross that a little bit like that. We sometimes don't know. We sometimes don't know. Okay, the only way we can find out if it actually start from above and then cross into below horizontal asymptote by doing the analysis we did just now, the sine graph against horizontal asymptote. Okay. Let me delete the highlight first, and then I put that 3 back. So it should be 3 here. Okay. So in this 1 hour, we actually went over 2 questions, but you will see it gets faster because what? I pretty much have taught you all the details. The main big questions are all these. Domain, y-intercept, x-intercept, vertical asymptote, horizontal asymptote. We have not done slant asymptote yet. Okay, but in between, I taught you how to know if the graph is above or below the x-axis, right? You perform the sine graph on the function, and you perform the sine graph on the function, right? This one here. And if you want to know if the graph above or below horizontal asymptote, you perform the fx minus horizontal asymptote. Okay, and in between, we also compute or learn how to find the coordinate of the hole. Okay, you plug the x that you are not allowed to put into the original function, but you are allowed to put into the simplified function. That's how we get the coordinate of the hole. Okay. Now let's go on with one more question without oblique asymptote, and then we do problems with oblique asymptote. Would you like to choose any question between number 20 to number 36? I hope you have your textbook with you to make that choice. Number 25, okay. Number 25. We have let fx be 2x squared minus 2x minus 4 big over x squared plus x minus 12. Let's factor them first. Okay, I will factor the 2 on the top. So I get x squared minus x minus 2. At the bottom, that will be x plus 4, x minus 3. The numerator I can factor further. That's x minus 2, x plus 1, x plus 4, x minus 3. Oh, nothing cancels, huh? It's already in simplified form. So no holes, right? No holes. Now, even if we can simplify, there is a chance we still don't have any hole. There's still a chance we don't have any hole. Okay, but we see that later on. You will feel it later on. You will feel it if it is a hole or a vertical asymptote. But for this one, it turns out to be on the easy side. The domain will be all real numbers except -4 and 3. And then how about the y-intercept? That will be 0,4 over 12. That's 1/3, right? F0 equals to -4 over -12. That's 1/3. Now, then the x-intercepts are 2, 0, -1, 0. Then part D, how about the vertical asymptote? Then we have two vertical asymptotes now, x equals to -4, x equals to 3. Horizontal asymptote, we get y equals to 2 over 1, or simply y equals to 2. Now let's take a look on the sine graph. Now I use other color because it's usually not being asked. But you still can do that on your scratch paper to help you when you try to sketch the graph. Okay, we have -4 as vertical asymptote, x equals to 3 as the vertical asymptote, that's undefined, right? And then 2, 0 is an x-intercept, -1, 0 also x-intercept. Now the y-intercept we already computed earlier. The y-intercept is positive, so when x equals to 0, that's positive, right? And all these critical numbers we had here, -4, -1, 2, and 3, are critical numbers with simple multiplicity of 1. So when we jump across that critical number, we change the sign. Okay, now beside using that critical number method, you can also do testing point, but usually testing point takes you longer time. Okay, now at this point, we can already sketch the graph, actually. Okay, oh, you know what? Let's do the sine graph against horizontal asymptote. Sine graph on horizontal asymptote. Give me a second. Sine graph on horizontal asymptote. So, but I need to do that first. That's 2x squared minus 2x minus 4 over x squared plus x minus 12. Subtract by the horizontal asymptote 2. Okay, 2x squared minus 2x minus 4 minus 2 times x squared plus x minus 12, big over the LCD x squared plus x minus 12. Okay, that's the function minus horizontal asymptote. Then gedebam, I simplify that fast. So I will get -4 plus 12, that's positive 8. So that's 8 over x plus 4, x minus 3. No, it's not 8. I'm sorry. 24 minus 4. That's 20. That's 20, not 8. I didn't see the 2. I didn't see this 2 here. Is it -4x minus 20? I don't think so. Oh yeah, that's right, -4x. I tried to skip steps and see that's what happened. Yeah, I didn't see that -2 and that's fatal. So I better just, now you see that you should just show the work, right? Okay, -4x plus 20. -4x plus 20. I can factor the 4 then. Factor -4 out, I get x minus 5. Oh, good thing I do the sine graph. So you see that we have critical numbers at -4, at 3, and at 5. Okay, that's 0 here, undefined here, undefined here. When x equals to 0, I get negative. So this is negative, this is positive, this is positive, this is negative. Okay, so at 5, it will intersect the horizontal asymptote, right? So we have horizontal asymptote intercept at 5, 2. The 5, I get it from here. Okay, the 2, that's from the horizontal asymptote. Okay. See, what happened here is we do little part here and there. Okay. So we know the y-intercept, x-intercept, vertical asymptote, horizontal asymptote, sine graph on the horizontal asymptote. We even have the horizontal asymptote intercept. Okay, but what our textbook doesn't really do is to put everything together. Okay, they just ask you to sketch the graph, right? But when they ask you to sketch the graph, they do give you the direction, the guidance on how to sketch the graph. Okay, you can see that on page 225, 226. Okay, but they don't really put everything in details like what I do here. Okay, what if? What if the graph actually intersect horizontal asymptote? How do we find where that is? How do we find the hole? Okay, and basically our textbook never really do the sine graph. Okay, which is actually quite helpful when we try to put them in details, which is what I'm about to do right now. Okay, so the following is the graph. We have a lot of things here though. Okay, we have vertical asymptote at x equals to -4. And x equals to 3. We have horizontal asymptote at y equals to 2. Okay, and then how about x-intercept, y-intercept? I forgot the details. X-intercept 2, 0, -1, 0. 2, 0, -1, 0. Those are the x-intercepts. And how about the y-intercept? 0, 1/3. 0, 1/3 here. Okay, now because I don't graph that on the coordinate system, then I will have to put I need to label it. So the y-intercept 0, 1/3, x-intercept 2, 0, 1, 0. Okay, now then let's start with the horizontal asymptote. Horizontal asymptote y equals to 2. Okay, now notice that to the left, this is the sine graph against horizontal asymptote. To the left of -4 is above that. So it is like this. Is it okay? Now between -4 to 3, it is below horizontal asymptote. Okay, but according to the sine graph of the function, between -4 to -1, it is below x-axis, 1 to 2 above, 2 to 3 is below. Usually, you can just use your instinct from there. Okay, you said x equals to -4 is a critical number with odd multiplicity, so it will change sign, right? And then it has to go through these 3 points here. Okay, and then x equals to 3 is a critical number with odd multiplicity. Okay, so it will go, supposed to go this way, right? Supposed to go this way. But I need to slow down a little bit. It turns out that we have a horizontal asymptote intercept at 5,2. So 5,2, we have horizontal asymptote intercept. So the graph actually looks like this. The graph actually looks like that. Okay, that's for this one question here. Now, let's take a break for 10 minutes. And then after that, we will do problems with oblique asymptote. Or if you have one more question, I still can answer that. We do problems with oblique asymptote, maybe 2 of them. And then we go further from there. Okay. I really hope I have chance to touch base 4.1, but if not, then we do it on Thursday. Okay, let's take a break for 10 minutes. We come back at 9:26. So for this page, I change it to 3.5 with horizontal asymptote. Okay, and after this, we will work on the problems with slant asymptote or curvilinear asymptotes. Okay, basically without horizontal asymptote. Now, we have not had a case where the horizontal asymptote is x-axis yet. Now, number 33 is one of them. Number 33, we have let fx be x minus 1 over x cubed minus 4x. Let factorize that completely first. At the bottom, we have x times x squared minus 4. That will be x minus 1 over x times x plus 2, x minus 2. So part A, the domain will be all real numbers except 0, -2, and 2. Oh, 0 is not in the domain. Okay, so there will be no y-intercept. Right? Because f0 is undefined. Right? f0 is undefined. How about x-intercept? So x-intercept will be 1, 0. Part D vertical asymptote will be x equals to 0, x equals to -2, x equals to 2. Part E, horizontal asymptote, the degree on the top is less than degree at the bottom, which means as x goes to infinity, this goes to infinity, but this goes to infinity a lot faster. Okay, the denominator goes to infinity a lot faster, and the quotient overall gets a lot smaller, very, very close to 0. Okay, that's the logic behind that. So that will be y equals to 0. Okay, let's take a look on the sine graph. Yeah, the horizontal asymptotes happens to be the x-axis. So the sine graph for this will also work for our sine graph against horizontal asymptote. Okay, so that's 0, that's 1, we have 2, we have -2 here, right? Okay, vertical asymptote and x-intercept here. The sine graph, this will be positive. You know what, I want to use red color. Now then, put them together. This will be the graph. We have no horizontal, oh, we have horizontal asymptotes. That's y equals to 0, which is the x-axis, right? Y equals to 0. Vertical asymptotes, we have x equals to 0, which is the y-axis. X equals to 2. And x equals to -2. X-intercept 1, 0. And from there, I need to play with the sine graph to know if it is above or below x-axis. Now, horizontal asymptotes above x-axis up to -2, right? This is above x-axis, right? Above x-axis, do you see that? Okay, now then between -2 to 0, it is below x-axis. Between 0 to 1, it is above x-axis. Actually, at 1, you have x-intercept there. Between 1 to 2, it is below x-axis. And then from 2 to infinity, it is above x-axis. So that's what the graph looks like. Now that's for number 33. It tends to be on the easy side because the sine graph also works for sine graph for horizontal asymptote. Okay, so we can see the x-intercepts at the same time where the graph intersect the horizontal asymptote. Okay, now that's 3.5 with horizontal asymptotes. Let's go on with, I open the new page so that that section is not too long, but the recording still one video, right? That's 3.5 without horizontal asymptote. Means either it has slant asymptote or it has a curvilinear asymptote. Okay, so a rational function without horizontal asymptote implies has either slant asymptote, a slant asymptote, or a curvilinear asymptote. Now, that rational function Rx has slant asymptote if the degree on the top is exactly equals to the degree one more than degree at the bottom. It have curvilinear asymptote if the degree on the top is more than one more than degree at the bottom. Okay, now let's deal with the one with curvilinear asymptote. Let's say number 37. As I remember, I did number 38 in the video. Okay, we have let fx equals to x squared minus x minus 6 over x plus 1. I factor the top. Okay, so we do the same procedure basically, right? For example, the domain will be all real numbers except -1. How about the y-intercept? The y-intercept is 0, -6, right? When x equals to 0, that's -6 over 1. How about the x-intercept? The x-intercept will be 3, 0, -2, 0. You have to factor them first. Okay, once you factor them, then these three informations, or a lot of informations, actually just basically you need to know where to look at. Okay, and the key is actually factoring the numerator and the denominator. Once they are in factor form, then A, B, C, D are actually easy to see. Okay, the vertical asymptote will be x equals to -1. Now, part E, horizontal asymptote is known. Y, the degree on the top is, which is 2, is greater than the degree at the bottom, which is 1. Okay, now then how about the slant asymptote? Since the degree on the top, which is 2, is 1 more than the degree at the bottom, which is 1, then fx has slant asymptote. Okay, the graph of fx has slant asymptote. How to find that slant asymptote? You basically divide. Okay, you divide the numerator by the denominator. Now, the nice thing is this rational function happens to divide by binomial x plus 1, right? So I can use synthetic division. So 1, -1, -6 divided by x plus 1. Now the quotient is your slant asymptote, y equals to x minus 2. -4, that's right. Okay. Now then, let's try to sketch this for now. Okay, at least let's see what we have at this point. Okay, we have the coordinate system. That coordinate system. And we have the y-intercept 0, -6. Again, I don't draw it to scale, so I need to label it. Okay, x-intercept 3, 0. Let's say it's approximately here. And -2, 0. So approximately here. Those are the x-intercepts. And then what else? The slant asymptote. Oh, vertical asymptote x equals to -1. So the vertical asymptote is x equals to -1. So approximately here. And the slant asymptote, y equals to x minus 2. Y equals to x minus 2. The slope is 1. Maybe a bit higher. The slope is 1. The y-intercept is -2. So that y equals to x minus 2 is this line here. Okay, now just like horizontal asymptote, slant asymptote is basically a horizontal asymptote that you slant. So you will see the graph later on here will be something look like this. Now, how do we know that that will be the graph time as well? First of all, I do it by instinct. It has to come from horizontal asymptote, right? Okay, I just follow this. So This one, why it's not going down like that? Because if it goes down like this, I won't have X-intercepts there, right? Okay, so you can actually argue using your intuition already, but suppose you don't want to do that, you want to be sure, then you do the sine graph. Okay, sine graph. We have on fx, that's the critical number are -1, -2, +3. -1, -2, +3. 0 here, 0 here, undefined here. The y-intercept is 0, -6. So negative, positive. This is positive. This is negative. Okay, so we see that the one above x-axis is in this interval above x-axis. Okay, and below x-axis are to the left of -2 and between 1 to 3. You see that? Now, actually, the new stuff, how do we know then that the graph is above or below the slant asymptote? But we did that work before. Okay, how do we know when the graph is above or below slant asymptote? Well, what we will do is do the sine graph on fx minus slant asymptote. Okay, the sine graph on that. Now, what is our fx again? Our fx is x squared minus x minus 6 over x plus 1. Now, subtract that by the slant asymptote x minus 2. LCD will be x plus 1. This is x squared minus x minus 6 minus x plus minus 2 x plus 1. So on the top, I will get -4 over x plus 1. Is it right? Something not right there. Okay, so when I do the sine graph here, we have only one critical numbers. Okay, and the sine graph here is positive. This will be negative. Okay, means to the left of -1, it will be above the slant asymptote. This is the slant asymptote, right? Now notice that to the left of x equals to -1, the graph is above slant asymptote, and to the right of -1, the graph is below the slant asymptote. Do you see that? Okay, so this is below the slant asymptote. Now, from the graph, by the way, here, can you tell what is the range of this function? I think it's quite easy, right? It's quite easy to see that the range of this function is all real numbers, right? Why? Because this goes indefinitely far below, it goes to -infinity, right? Okay, and it goes to positive infinity here, and you have everything in between. So even if I use only this part here, the range is already all real numbers, right? Okay, the range is already all real numbers. See, notice that I don't really ask that question, the range, but you will be able to tell the range after you finish graphing it. Yeah, sometimes you cannot say anything though. So yes, sometimes we just don't have any way to find out the range. But in this case, we happen to be able to tell, right? Okay, like say the one here. I go back to the question we did with horizontal asymptote at y equals to 0. Okay, what is the range for this function? You just need to look at this guy here. This goes to positive infinity, from positive infinity, negative infinity, right? Okay, so using that one graph only, that one piece of graph only, we know the range will be all real numbers. Okay, this one here, maybe not. The one here, I don't think, the one here, I don't think the range is all real numbers. I don't think so. I don't think we have a way to find out though, for this one question here. But let me save it for now. Okay, let me save it for now. I will take a look later on if it is actually doable. I don't think it's doable for this one. The one here, we did find the range for this, right? Yeah, we did find the range for this. Number 18, did we? Oh, can you find the range for this one? Oh, I do it later. Okay, this one is what, number 18. Yeah, so I will show you how to find the range for number 18 later on. But let's go back here first. Yeah. It's not something we always get though. Okay, don't get me wrong. There are times that we cannot find the range at all. Like in earlier number, what? I think number 25, we cannot find the range at all for number 25. Yeah, it's too difficult to do. It's too difficult to do. Okay, let's do one more, number 39. The one with slant asymptote. Number 39, we have fx let fx equals to 8 minus x cubed over 2x squared. Now, because the denominator is not in linear form, then we cannot do syntactic division. Yet, because it is only one term, we can split that and simplify further from there. So this is 4 over x squared minus x over 2. Okay, so the domain will be all real numbers except 0. And because 0 is not in the domain, then we won't have y-intercept. How about the x-intercept? Then we set the numerator becomes 0. Right? So x cubed equals to 8. X equals to cube root of 8, which is 2. So x-intercept is 2, 0. And then part D, how about the vertical asymptote? That's x equals to 0. Horizontal asymptote. Degree on the top is more, right? So there's none. How about the slant asymptote? The degree on the top is exactly 1 more, right? So I will do, actually, yeah, I supposed to do this long division here, negative x cubed plus 0x squared plus 0x plus 8 divided by 2x squared. Okay. But you will see, because I did it this way here, and I get that the slant asymptote will be just this guy. Well, anyway, let me just do this. This will be negative 1/2 x to give me negative x cubed, right? And then I have remainder 8. So the slant asymptote is given by y equals to negative 1/2 x. Okay, how about the sine graph? This is f, by the way, not d. How about the sine graph? We have critical numbers at 0. Actually, there's a critical number with multiplicity of 2. And x equals to 2 is a critical number with multiplicity of 1. This is negative, this is positive, this is still positive. Okay, so if I sketch the graph, we have X-intercept 2, 0. I don't think we have Y-intercept. We have vertical asymptote at x equals to 0. And slant asymptote y equals to 1/2 x. Y equals to 1/2 x, it looks like this. The slope is negative 1/2. Okay, now according to the sine graph I have, it will be positive here. And x equals to 0 is a critical number with even multiplicity. So that's the same sign. And it will go this way. That's what the graph looks like. No holes, right? No holes. That's what the graph looks like. And actually from here, you also see that the graph will always be above the slant asymptote. Let's show from the sine graph. Okay. Sine graph against horizontal asymptote. We have fx, which is 8 minus x cubed over 2x squared minus the slant asymptote 1/2 x. That is 8 minus x cubed over 2x squared plus x over 2. So you will get 8 over 2x squared, which is 4 over x squared. So you see the sine graph will have critical number 0. But to the left and to the right are positive. Okay, so to the left of x equals to 0, the graph will be above slant asymptote. And to the right of x equals to 0, the graph also above the slant asymptote. Now, can you tell what is the range? Okay, think about this. If we can answer the question of the range, you should try to find the range. Okay, you should try to find the range. Now, in this case, of course, this goes to positive infinity, right? And this continues. And this goes to negative infinity. Okay, remember the idea of far ends behavior, right? Now this horizontal asymptote, slant asymptote, curved linear asymptotes give us the far end behavior actually. Yeah, so the range here is all real numbers. That's right. The range here is all real numbers. Okay, I will do one more question, this time on curved linear asymptote. The sine graph before this one. The one here? Sine graph for the horizontal as okay, sorry, I wrote it wrong. This is sine graph on slant asymptote. Before the one slant asymptote is this one. I basically use this. I use this one to get that one. Okay, good. Now let's go on. What happens if we have curved linear asymptote? That's if the degree on the top is at least 2 more than the degree at the bottom. Let's say, for example, number 41. We have let the function fx equals to x to the 4th minus x squared minus 5 over x squared minus 2. Now, the question for this number 41 only find the curved linear asymptote. So that's what I will do first. Let's do that one first. Okay, what is the curved linear asymptote? Okay, it comes from the word curve asymptote. Okay, it's so in the asymptote instead of just instead of a line. Usually, the word asymptote actually refers to a line. Okay, but we make an exception here. The asymptote is not a line but a curve. Now, how do we find that curve to which this function approach as it goes to infinity and negative infinity? We do it by dividing, by actually dividing. X to the 4th plus 0x cubed minus x squared plus 0x minus 5 divided by x squared minus 2. That will be x squared when I subtract, this cancel, we get -1 minus -2, that's +1. So this is x squared plus 0x minus 5, that's +1 for x squared minus 2. So the curved linear asymptote is y equals to x squared plus 1. Now, in other words, the graph later on, let me put it here first. So we have this coordinate system. Okay, and the curved linear asymptote look like this. Let's say that's what it looks like. X squared plus 1, right? Okay, now then when you go very far to the negative infinity, the graph get closer to this hand. When you go very far to the positive infinity, the graph get closer to this hand. What happened in between, we don't know. Okay, but we know the right hand behavior will be infinity, left hand behavior will be positive infinity also. Now let's fill in the details then. Okay, for example, For example, let me write the function again here. Fx equals to x to the fourth minus x squared minus 5 big over x squared minus 2. Now then part A, what's the domain? I cannot factor it, but I still can solve it, right? That it's all real number except radical 2, negative radical 2. Is it right? Because x squared minus 2 cannot be 0. Part B, what is the y-intercept? The y-intercept will be 0, 5 over 2, 2.5. Oh, okay, so if that's the case, we have the y-intercept 0, 2.5. Okay, the graph will pass that one. How about the x-intercepts? We have x to the fourth minus x squared minus 5. Set it equals to 0. I use quadratic-like equation. So u squared minus u minus 5 equals to 0. Okay, I don't think I can factor it. I will use quadratic formula. So u12 will be negative b plus minus square root of b squared minus 4ac over 2 times 1. That's 1 plus minus square root of 21 over 2. So u1 is the positive branch. u2 is the negative branch. But that guy is negative though. Okay, so x squared equals to that has no real solution. For this one, however, there's a positive branch, not positive minus. For this positive branch here, then that's our x squared, right? So x will be plus minus square root of 1 plus square root of 21 over 2. So that's plus minus 1/2 square root of 2 plus 2 square root of, I'm sorry, multiply the top and the bottom by 2. Yeah, like that. So if I go back to my x-intercept here, I will have x-intercept somewhere here and somewhere. And in fact, if you think about this function, if you look at this function is an even function, right? Try to replace x by negative x. You will see you get exactly the same function, right? So it is symmetric with respect to the y-axis, right? Okay, now then this will be 1/2 square root of 2 plus 2 square root of 21. This is negative 1/2 square root of 2 plus 2 square root of 21. Those are our x-intercepts. Vertical asymptotes, where should I put it? Let me put it here. Vertical asymptote, x squared minus 2, the denominator 0, so we get x equals to plus minus square root of 2. Plus minus square root of 2, if I look at this, it will be here. This is x equals square root of 2. This is x equals negative square root of 2. Now, can we put details to this? Oh, yeah, well, it will look like this. Then it follow this and slowly goes down there. Okay, and then this will go this way. And this will go this way. Okay, now let's try to graph this, use a graphing software to see this better. Okay, yeah, I know I did it right, but in case you want to see what the shape look like, let's take a look. So y equals to, let me change you to my graphing software, x to the fourth minus x squared minus 5, all of them divided by x squared minus 2. That's what it looks like. Okay, now when you go to the curved linear asymptotes, you basically zoom it out so far. If you zoom it so far, that's the graph of x squared plus 1. When you zoom it out very, very far, right? Okay, that's the graph of x squared plus 1. From far away, let me put one more equation. Y equals to x squared plus 1. You see, they coincide, right? But when we zoom it in, it turns out that it only followed that red graph, which is x squared plus 1, when x is very big to infinity, the very big positive x, positive infinity, a big number positive or a big number negative. Okay, but when we zoom it in around 0, the graph of that rational function differs significantly from the graph of that quadratic function. Okay, so you see how we take use of the curved linear asymptote to give us the guiding lines or the guiding curve to which the graph will approach when x is big infinity, big positive, or big negative. Okay. That's the graph. Okay. Now the thing is, if you try to use your graphing calculator to graph that, I don't think you can get this though. You won't be able to graph the curved linear asymptotes. You won't be able to get that one. You see, you won't be able to get that one. Okay. Now that's only one curved linear asymptotes that I can do. Let's do one more, number 48, and I hope that's the last question for the day. Number 48. Let fx equals to x cubed minus 2x squared minus 4x plus 8 over x minus 2. Oh, this question actually on the easy side. This question may be on the easy side. Okay, let's see. Let's factor the numerator first. If I factor the numerator by grouping, okay, so that will be, I have common factor x minus 2, so I get x squared minus 4. Notice that they cancel, right? Right. Okay, so fx now is equal to the simplified version, which is x squared minus 4 for x not equals to 2. Oh, I thought that's a hard question. It turns out to be an easy question. It's undefined for x equals to 2. So what is the graph of this function? Well, the graph of this function is basically the graph of this function with a hole at 2. Okay? Like, for example, okay, so what is the domain? The domain will be all real numbers except 2. The y-intercept is 0, -4. The x-intercept will be supposedly -2, 0, and 2, 0, right? But 2 is not in the domain. So we have only one x-intercept. Do we have horizontal asymptote, vertical asymptote? None. Why not? Because in the simplified version, we don't have any 0 on the denominator. How about horizontal asymptote? None. Also because the degree on the top is more than the degree at the bottom. Do we have slant asymptote? We also have none. Because the degree on the top is more than 1 more than the denominator. The difference of the degrees is 2 or more. Okay, now do we have curved linear asymptotes? We happen to have that. When we divide, we get y equals to x squared minus 4. Okay, now what will the graph look like? This happens to be, again, it happens to be on the easy side. That's the graph of x squared minus 4. The graph of x squared minus 4, except it is a hole at 2. Like that. That's basically it. Okay, I thought this question is hard. It turns out to be on the easy side. Okay, last one. We have approximately 10 minutes left. Let's think about number 54. So we go backward right now. Number 54, they give us the ingredient of the graph of the functions, like the vertical asymptote is x equals to -1, x equals to 3. Horizontal asymptote is y equals to 2. And x-intercepts are -2, 0, 1, 0. And they have hole at x equals to 0. Now the thing is, from here, can we find the function? So we reverse engineer that. Okay, let's start. Solution. The vertical asymptote is x equals to -1, x equals to 3, which means x plus 1 and x minus 3 is are factors of the denominator. Right? Okay, so at this point, we can say that our function, our rational function, has this on the denominator. Is it okay? Now, horizontal asymptote is 2. Y equals to 2, which means the degree on the top and the bottom are the same. Degree of the numerator, let me use n is equals to m, right? But we still don't know what degree. We just know that degree must be the same such that the ratio of the leading coefficient is 2/1. Then we have x-intercepts are -2, 0, 1, 0, which means the zeros of the numerators are x equals to -2 and x equals to 1, which implies x plus 2 and x minus 1 are factors of numerator. So we have x plus 2, x minus 1. So let me color that. Vertical asymptote give us this. Horizontal asymptote give us this. Okay, x-intercept gives us this. Okay, but we still have extra information. We have whole at x equals to 0 means x is a factor for both numerator and denominator. Okay, so it is x to some power and x to some power, and let's call that x to blah, x to the c, x to the c. They just tell us it is a whole there though. Okay, now, but if we want to talk about the minimum degree of rational functions that give you these informations, then you just need x and x there. Okay, so the functions now is equal to fx is equal to 2 times x squared plus x minus 2 over, I'm sorry, I have another x here, over x times x squared minus 2x minus 3, which is 2x cubed plus 2x squared minus 4x over x cubed minus 2x squared minus 3x. That's what the function looked like. Okay, now on Thursday we will go on with 4.1 inverse function, and after we're done with that inverse function, I will do hopefully exponential functions, at least part of that. That's what I plan to do on Tuesday, but I'm basically done with the rational functions. So tomorrow on Monday, Wednesday class, I will go over the all test problems in regards of rational functions. Okay, now yesterday we already did problems from all test 2 in regard of polynomial. So tomorrow will be on the rational function. On Monday, it will be on inverse function and maybe exponential function. Okay, then that's for today. See you on Thursday.
Thank you, Professor.
You're very welcome.